if you remember in the last lecture, so it's audible, ma'am? Am I audible?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Thank you. Thank you. So in the last lecture, we were looking for the solution of where is
Initial
my
value
pen?
problem.
Yeah. For the first order initial value problem, y prime is equal to fxy with the initial condition y at where x naught is any point in the domain of the differential equation, y at x naught is equal to y naught, and we assume that let y be a solution of this initial value problem. So then we were looking for yx. We kept yx on the left hand side, and we are looking the right hand side as a given quantity. If we would be able to find the right hand side in the given term, so then our work is over and we are able to solve that. But as I told you in the beginning that we don't have any procedure by which we can find the exact solution of this first order initial value problem in the journal form. Means take any value of f, of course certainly with satisfying the existence uniqueness property of the solution. So even then we don't have any procedure, so it means that it would not be easy to keep the known thing on the right hand side. So there will be certain issue would be there, and to settle these issue, so we will make some approximation. So that's why we will study these method under the umbrella of numerical analysis. Yes, somebody was saying something. Yeah, so my basic motive, so what are the given thing? Actually x is given here because x is a independent variable. X is given, f is given, and y naught is given, means the value of y at x naught is given. So now what should I do, means how we should move. So basically we should convert this y thing, y at x, rather y at x naught. So then things would be somehow known there initially. So I involve x naught, I add x naught and subtract, and in that case there is no harm in doing that. So I add x naught and subtract x naught. This thing is clear. I know x, but I don't know the value of y at x. So now my objective, I don't know y at x naught, but I know y at x. I don't know y at x, but I know y at x naught. So using the Taylor's method, Taylor series method, I will expand this around x naught. So this is y at, I use Taylor's series. I will expand this y at x naught plus x minus x naught. Suppose I am denoting this by h. So basically this is equal to y at x naught plus h.
X.
So now of course h depend on x because x naught is fixed. So what we have the first term is y at x naught plus h time h y prime. Hello.
Yes, sir.
Yes.
Yeah. Somebody was saying something.
No,
sir. Y dash x naught.
Y. Yeah. Okay. Just y dash at x naught plus h square by
H square by 2
Factorial.
factorial or f double y double dash
y double dash at
x naught.
x. Yeah, in that way. So we have now look, we can write the journal term dot or we can write this in a remainder form
H
h
key power n
n
upon n factorial
upon n factorial y n at x naught, and we will write the last error term as h
key power n
n
minus 1 n minus
n plus
1
n plus 1 divided by
n plus 1 factorial
y at n plus 1 at derivative at xi, where xi belong to the interval around x naught. So in that way we have written this, otherwise it has the infinitely many terms. So whatever the rest term is there, so that contribution is taken care of this one. So this thing, so now we will look at what are the quantity which we are aware, in this thing. So if we look the first one, so y at x naught is given, am I right? It is known, so nothing to worry because it is given. This is y naught. Now we are coming to the second term. In second term we have 2 h and y prime at x naught. So tell me whether h is given to us or no. Anybody can answer?
Sir, arbitrary.
Yeah, h is known or not? Hello. Yes, somebody answered. Yeah, h is known because h is equal to x minus x naught. So x is also independent. So where we are looking for the value of unknown parameter, so that is, or unknown, that is given to us. So this is x is known, x naught is known, because these are the independent variable. So h is known. Now we are coming to y prime at x naught. So y prime at x naught is given.
Yes, sir.
Yeah, well, from the differential equation we can find. Am I right? So it means that if we look here, so this is y naught plus h, h is also given, and y prime at x naught is f naught. F naught means f at x naught comma y naught. So this is given. Now we are coming to the third one, whether this y double prime at x naught is known because f is known to us. So these two terms are now known to us. So now we talk about the third one. Anybody can answer? H is known, so of course h squared by 2 is also known. So now we are just caring about this y double prime at x naught. So whether it's given, hello, yeah, y double prime we can write. Yeah, y double prime can be written as, first we will write y double prime x and then we will replace x by x dash naught. Yeah, x naught. So dy by dx of dy by dx of y prime, and y prime is nothing but f. Am I right? And f is a function of two variable x and y. So we can find its value because f is known. So we can find its value by the chain rule. So just quickly tell me the what will be the value of f, dy by dx of f. Please tell me. Quickly calculate. All of you should calculate and tell me. So we have h squared by 2 what happened? No. Where is my pen? Go. Yeah, so just quickly calculate this y double prime and tell me by curly f by curly x into dx by dx plus curly f by curly y into dy by d by dx, dy by dx. Am I right? So I'm not able to write here. So where is this pen? How it will, okay, yeah. So so this is 2, and tell me what value we are getting for y double prime. So f x means curly f by partial derivative of f with respect to x into dy by dx, dx by dx1 plus curly f by curly y, partial derivative of f with respect to y into dy by dx means y prime, which is again f. This thing is clear. So yes, we are getting this at x naught. Am I right? At x naught. This thing is clear. So f is known. If f is known, so its partial derivatives are we can calculate. So it means that the third term is also known. Now go for the fourth term. What will be the fourth term? Will be h cube by factorial 3, or we can write directly 6, whatever you are writing, and then quickly do one, what will be the y triple prime? Y triple prime is equal to y triple prime is equal to dy by dx of y double prime, dy by dx of
fx plus fy of x.
yeah, fx plus. So just quickly calculate
F
that all,
double
and
fx
simplify.
plus f of xy into
Yeah, f, just tell me f
xx plus
fxx. So did you calculate on your notebook? Quickly do that and tell me the simplified one. Plus so anybody calculated?
So 2 times of mixed derivative fxy plus fyy.
2 into
2 times mixed derivative fxy
fxy
plus fyy.
plus fy means the
At x equal to x naught.
yeah, at x equal to x.
ये सब पढ़ा हुआ है. Your writing is not visible, sir.
Screen is not visible.
We can see
Visible.
your screen. It's visible, sir.
Yeah, so in that way we can find, if you look, I mean, if we go for the fourth derivative, means fifth term, so that can also be calculated. Am I right in that way? So now, I mean, you would say that, sir, okay, everything on the right hand side seems to be known. Am I right? Because every term we can calculate. Of course, we put the restriction on f, that it has it is sufficiently smooth, or it has the desired regularity, means its derivative exists. But I mean, on the right hand side, everything is known to us. Am I right? So you would say that, sir, but you claim that we don't have any procedure to find the exact solution of the problem, and in that way we done that. But here the problem is that we don't have any procedure to sum of this infinite series. We can sum this infinite series in a particular cases, but in journal we don't have any procedure. So that's why we आसमान से गिरे खजूर पे लटक गए. Am I right? So what we need to do now? We need to now truncate. Am I right? This series, or we will count only the finitely many term of the series that can be sum up. Am I right? So in that way we have, and whatever, I mean, if we keep one term of the series, so then we will have one method. If we keep two term of the series, two term of the series, so then we will have another method. If we keep three term of the series, then we have another method. So in that way, using this approach is known as the Taylor series approach. Is known as the Taylor series approach, and by this approach we can generate a family of methods. Am I right? So now we should look some property of this type of method. If you look here, so And what will be the error in this case? Suppose I keep 3 terms of the series, so then order will then error will be this one, means HQ by 6, and it's I mean unknown fourth derivative at xi. So this will give us the error. Am I right? So what is the beauty of this approach? The beauty of this approach is that we can generate a method based on Taylor's series method, Taylor's approach with desired accuracy. Am I right? If suppose we generate a method keeping 2 terms, and then we compute the approximate solution, we feel that the approximate solution is does not have the desired accuracy, so we can take another one, we can take 3 terms, so then of course we will have the better. And so in that way, if after keeping 3 terms in the method and we are not getting the desired accuracy, so we can have the 4th term. So it means that we can have the desired, we can generate a method with desired accuracy based on Taylor's approach. This, are you agree?
Yes, sir.
So I think this is the most desirable condition in the approximation theory. Am I right? If somebody say that, okay, I will give you the approximate solution, and with the rider that, or with your desired accuracy. So then what else you want? So it means we should think here, then why the other method came into the picture, like Picard method. Did you heard Picard method for the initial value problem? And Picard method, modified Euler method, Euler method, modified Euler method, trapezoidal method, Rangakuta method. So then what is the fun for searching these type of methods? So we have to have some drawback of Taylor's method, which encouraged us that time to generate some other class of method. Am I right? So anybody can answer? Anybody can tell some drawback of Taylor's based method?
Here we need to find the many functions derivative of functions.
We need to find, please speak loudly.
Yes, we need to find many function evaluations, means derivative, many derivatives.
Yeah, we need to compute the derivative. Am I right? We need to compute the derivatives. Am I right? So we need to compute the derivative, and particularly it's fine for the scalar when we are considering this scalar initial value problem. But when we have a system of first order initial value problem, so in that case these derivatives will convert to a Jacobian, and it's a full matrix. Am I right? So it's a very cumbersome. Even we would be, even in this case also, if you go for the y4 or y5th derivative, so then it seems to be cumbersome. But okay, chalo, nowadays we have the machine to do that. But when we go for the system of equations, so in that case, when we compute the Jacobian, means the derivative, so there Jacobians comes into the picture, and to compute that, it's very computationally costly. And if we have a very big system of equation, so then in that case, sometime our supercomputer will not work. So that's why we are not interested to compute the derivative. So then we come to the second approach. I don't think that I need to give you some example for solving that. Even I can give you in the assignment. I can give you in the assignment, so you can do practice. So I'm just giving here the flavor that how the research might have evolved when it was done that during that period. Or you should think that how we should approach to solve our problem. So first we should narrow down our problem, or we should concentrate that what are the drawback, and then how we should tackle this. For example, as we start from here, am I right? So in that way we should work. So now our problem is that we wish to get rid of these derivatives. So the basic tool to get rid of derivative is so the to get rid of the derivative is the integration. Am I right? So now we will integrate this initial value or differential equation y prime is equal to fxy from x naught to x naught to x. So please integrate that on your notebook. So what we are getting yx yx is equal to please do that quickly. I'm just writing the one y at x naught y at x naught plus x naught to x. Am I right? F x comma y dx. This thing is clear. So to get rid of the derivative, the best way, just integrate that, and we have done that. So now look on the right hand yx. Of course, it's a solution of the initial value problem. So we are looking for that. Now we are looking the second term. Second term is known to us. Now tell me whether we can find this integral or not. Please answer. Hello.
Yes,
Yeah,
sir.
of course, in journal we cannot find this. Am I right? So then we should look that where is the problem. We are generating here the Picard method. Picard's method. So now tell me that what is creating a problem here. Here this y unknown is sitting in the right hand side under the integral sign. So this is basically creating a problem. Am I right?
Yes, sir.
Yeah. So then what we will do, we will basically generate a sequence approximation, and of course you might have studied in the existence and uniqueness of the solution of this initial value problem, that sequence converges to the exact solution. Am I right? Why? We keep so how we generate a sequence? Anybody can answer? In that way we will do that. basically for generating a sequence, what we require. Yeah, just just give answer whatever you feel. It's not necessary that you will have or any everybody.
Sir, we need y1, y2, y3 and so on.
Yeah. So, but we cannot write infinitely many terms. So that's why what we require one recurrence
relation.
Yeah, one recurrence relation and first term of the sequence. So how we will generate a recurrence relation here? So we keep unknown on the nth place. Am I right? This is
Yes,
y
sir.
naught plus and this whatever sitting this
Y n minus 1.
yeah at n minus
1.
1 x naught to
X.
x f fx
Comma y n minus 1.
y n
Minus
minus n minus 1 dx. And also, as I told you, that we also require the first term of the sequence. Now our sequence is this one, y n. Am I right? So I require y0 also. So what is y0? Y0 I am taking y at x naught. Y at x naught, which is given to us. So now we have this sequence. Am I right?
yes, yes.
Yes, sir.
Now this sequence is known, and we know the at, or we can easily prove that this as n tends to infinity, this sequence converges to yx, which is a solution of the initial value problem. Am I right?
Yes, sir.
Yes.
Yeah. So it means that as n tends to as n is bigger and bigger, so the term of the sequence will be closer to the exact one. Am I right? So in that way, we will generate a sequence of approximation, and each member of the sequence is an approximation to yx. This thing is clear. So if we take one first term of the sequence, so then we will get an approximate value to the unknown. If we will have y2, so that will give a better than y1, y3 better than y2, and in that way this thing is clear. So in the beauty of Taylor's approximation we retain, and of course here we need not to compute the derivatives. Am I right? So we will get rid of the computing the derivatives, and we retain the beauty of the Taylor's approach, that this approach also give us answer with the or approximation with the desired accuracy. Am I right? So you should say now that now I think we should stop searching other method, but still we are aware that there are certain other method also. Euler method, modified Euler method, trapezoidal method, Rangakuta method, multi-step method. So anybody can now draw back of these two or this class of method? Anybody can answer? So basically, what we are doing, we are approximating the function fx comma yx by another function in the interval x naught to x. Am I right? Or if we just come back to the Taylor's method. So what was the Taylor's method basically? In the Taylor's method, the yx is given or error in the Taylor's method, if I call it rather. The error in the, even here also we can explain, but by the Taylor series we can easily, error is after keeping the n term. So error is h power n plus 1 means h is x minus x naught power n plus 1 divide into y n plus 1 derivative h hi divide by n plus divide by n plus 1 factorial, n plus 1 factorial. This thing is clear. And let us assume, as I told you, that we have this y is sufficiently smooth. So let's assume that y belongs to c n plus 1 c n plus 1 on I, means it's nth derivative, n plus 1th derivative exists, and continuous means it is bounded. So suppose let us assume that y n plus 1 x xi is bounded by m. So then this will replace by the bound, means capital M, where capital M is the bound of the derivative n plus 1th, and this inequality will become inequality. So error will be less than equal to x minus x naught n plus power n plus 1 m n plus 1 factorial. This thing is clear. So now look on which now error depend. Error depend on this term. Are you agree?
Yes,
If x is far from x naught, so then error will be more. Am I right? If x is far from x naught, so then error will, or as x increases, or as x minus x increasing, the error is keeping increasing. What does it mean? It means that if we simulate any our problem for longer time, our result going to be worse and worse. So it means we can say that. So same thing will apply in the Picard also, because in Picard also basically we are taking approximation. We are approximating this function fxy by fxyn. Am I right? In the interval x0 to x. So if this interval is going to be bigger and bigger, so then this approximation will be worse and worse. You might be aware about in the Riemann integral, in Riemann integral, basically what we do, rather taking approximation in a bigger interval, we divide that into a small subinterval and then take the approximation. Am I right? So if we take approximation in a bigger interval, so then it would be worse. This thing is clear. So that's why these all both the method, this class of method, which is known as the closed approximate methods, are biased towards the initial value or initial node. These methods are biased towards the initial node.
Another below node.
So it means that these method are biased, but we are interested to develop the method which gives us uniform result or uniform error on the entire domain. Am I right? So that this drawback of this class of method give us further give us to research the other methods which are known as the discretization method or step marching method. Step marching method. Step marching. Step marching. Step marching method or discretization method. Discretization method. This thing is clear. So anybody have any doubt till here?
No, sir.
Yeah. So what we do, first, as I have given you the hint that what is creating a problem now here, because we are taking approximation on a bigger interval. So now what we will do that we will divide our domain. We will divide our domain into a small pieces or small subintervals, and then take approximation on the smaller part. Am I right? So in that way we will get rid of this problem. So first we should identify what is the problem, and then we should answer that. So our problem is that because we are taking approximation on the entire domain, x0 to x. So now what we will do, first we will discretize the domain. Suppose this is our domain. This is x node, and this is say capital X. This is capital X. So what we will do, we will discretize the domain, or we will go basically we have to solve problem on the entire domain, means x0 to capital X. Am I right? But how we will move that? We will discretize the domain into a small interval, and then taking approximation from here to here, we will reach here. Then using this value, we will reach here. Using this value, we will reach here. Here it is giving y naught. Using this value, we will predict this one, y1. Using this y1 now, we will predict y2, and so on. This thing is clear. Suppose this is xn. So xn is equal to capital x. So in that way, we will get rid of that. And this class of method is known as the step marching. Why step marching? Because we are moving step by step rather than jumping from here to here. We are going in small steps. Am I right? And then we are reaching to the final one. Or discretization method, because basically what we are doing, we are doing that the discretization of the domain, entire domain. We divided the entire domain into a small pieces. This thing is clear?
Yes, sir.
Yeah. Now this step marching method are classified into two classes: single step and multi-step. Multi-step. Okay, I'm running a new one. So suppose we have this is our domain basically. Am I right? So what we are doing? We are doing, suppose this is X node, and this is our capital X, and at X node I know the value, and now we are moving step by step using the Y1 and Y node. We are predicting the value at X1, say it is Y1, then using Y1 we are predicting this at Y2, and of course these step also may vary. It may be uniform step size or it may be vary. So certain thing could be X3, Y3, using Y4, predict X4, the value at X4. So now we have Y3 with us. I know the value at X3, we know the value at X2, we know the value at X1. When I am predicting the value at X1, so then I have only the one value at Y1. But when I'm predicting the value at X node, so now we have Y0, Y1. Now, when I'm predicting Y at value at X3, so then I have Y0, Y1, Y2. Am I right? Hello? Yeah. So in that way, in that way, when I'm predicting at X4, so of course I can use only the previous value, then we can get that also. So if we are using only the one value, so then it's fine. So we have the single step. To predicting the next, we are using only one step. But as you know that if you have more information, you use more information for the prediction. So of course you would have the better result. Am I right? Also in that way, suppose you are using now Y2 also, Y2, Y3 for predicting at X4. So now you are using two step. So it means that then your method will be two step. Am I right? Two step. If you are using three step to predict Y4, so then your method will be three step. If you are using K step for predicting the next value, so then method will be K step, and these are known as the common data multi step method. So tomorrow first we will study the single step method, and then we will move to multi-step method. So today homework or assignment is that at least you people should do two example for Taylor's and Picard method. You should just, so then you will be able to see, you can take any book. You can take MK Jain, or you can take Burden and Fear from any book, or Lambert. I'm afraid that you would have this some numerical examples, some theoretical things would be there. So at least then you would be able to visualize that what we have done. So I think I should stop here. So any doubt, anybody have any query? So I can answer. We have a few minutes. Yeah, ma'am.
Yes,
Okay.
participants, you can ask your questions from anyone.
No question,
No
sir.
question. Okay, sir. Thank you so much.
Okay. Thank you, ma'am. Thank you.